Good day everyone. So due to the corona outbreak in Sri Lanka, and we have to conduct the lectures through the internet. So yeah, because of that, I'm going to do this week's lesson. I'm going to record it as a video and share it with you guys so we can continue with our lesson plans uninterrupted. Alright, so this week's topic is the shaders and materials. So first, what's the difference? Let's try to understand the difference between a shader and a material. So actually, a material is something that we apply to a geometry in a game engine, or actually not just in a game engine, maybe in any 3D program, to define how does the surface of an object is rendered. How does the surface of an object displayed in that game world. And the material, so material may contain some attributes like colors, shininess, normals. It can be depending on the implementation. It will have a set of attributes, and a shader is a program that allows material to be rendered at the runtime. So that means material defines the set of attributes, and using those attributes, shader runs some program, maybe in a GPU, to actually render that using those instructions, using those attributes, actually rendering that object into the screen. So yeah, a program runs on GPU usually, defines colors, lighting, shadows, details of each pixel in the screen. So yeah, if you don't know what GPU means, that means graphics processing unit. Usually we call it VGA card. So this is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended for output to a display device. So there are NVIDIA GPUs and Radeon GPUs, and also Intel GPUs. So yeah, those are these things that we are talking about here, right? So yeah, in order to understand writing codes to run in GPUs, we have to understand a little bit about its architecture. So we usually we are used to write programs for CPUs. That means we are used to think of programs more in a sequential manner rather than a parallel manner. So a CPU is a latency optimized fast serial processing. That means a CPU is optimized to do serial processing tasks as fast as it can. Even though CPU can support parallel processing, so this is optimized to execute one instruction and go to the next, so do that as fast as it can. But the GPU is throughput optimized fast parallel processing. So GPU or graphics processing units, this is designed in a way to maximize the throughput of that processor. That means it's like rendering as many as pixels simultaneously. So this is more like parallel compared to the CPU. So for example, GPU wants to render all the pixels of the screen. So we can consider rendering. Actually that means determining the color value of a given pixel on the display. So those that rendering of each pixel can be parallel, because most of the time we are able to determine a color of a single pixel without knowing anything about what are the values of surrounding pixels. It's not a perfect example, but you can think of it like that. But the CPU, the things we need to do in CPU are usually not like that. In most cases it depends on the values that we get maybe in a previous step. So yeah, that's why I said GPU is more parallel. All right, GPU parallel processing. This is what I explained in the last episode, in the last slide. Position XY and gives color in RGB. We give the position of the screen, that XY represents the index of pixel in X coordinate and Y coordinate, and it gives a value, color, and RGB value. So that is the base rendering function. That's what actually rendering means. And shader is executed all at once for each pixel in the screen. Parallel. So yeah, examples for serial and parallel. So a printer, maybe it can print a single line simultaneously, and for a modem it can transmit zeros and ones in a serial manner or a sequential manner. For example, think about serial communication, something like this, and it's like the vision and hearing. So for hearing, we need to hear like words one after another. For example, just think of a sentence like I am Tilina. So to make sense of that sentence, we need to first listen I and am Tilina. So we should hear them in that order. But if I hear all the words in that sentence at the same time, it wouldn't make any sense. So that's more like a serial thing. So for parallel, it's we can think of it like the vision. So when we see something, we see all the points of that object at the same time. So there is no particular order. Like for example, just think about looking at this slide. So it's not like that we should first see the top left corner of the screen, and then this one, and then the second one, and this one. So like that, there is no order to that. We can just look at the screen at the same time about all at all points. So it's more parallel, right? So I have a small exercise. Let me load. There is a site called Shader Toy. So if you're following this lecture, I recommend you to also go to this shadertoy.com and you can follow along. So this is Shader Toy. So this is to just to practice how to write some programs, write some shaders. So actually this may be different from the actual shader GLSL language. I'm not sure about that, but we can this is good to understand the concept. So I'll get a new file. So when I get a new file, this is the output of this code. So this void main image, this is like the function we can give the position of the screen in this in vector2 frag code parameter, and this would be the returning value out vector4 frag color. So when we give the position of the pixel, it will return the color of the parameter and the color of that pixel. Okay, so first let's do something like this. This is the output to the screen. I'll delete this too. And then I have to delete this one too. So I'll return, this is a vector4, so I think that should stands for RGB, and I'm not sure the other one is alpha. Let's see. So let's first return 0 0 0 0. So whatever the value whatever the position of the pixel, I'm returning 0 0 0. Now let's compile this. Right, now we get a complete black screen, and yeah, this one should be alpha. So but even if I make it 1, it wouldn't be any difference, because we don't have anything beyond anything after this layer, so I think it wouldn't make any sense here. Right, so yeah, I'll make it like this. Now if I make this 1, that means this is R is 1, so this should be all red. Yeah, what happens if I make it 1 again? Nothing. Okay, so the red value is 1, and now just to make this clear, I'll make the G value also 1, and it becomes green. Let's make it 0 again, and blue value 1. Now all should become blue. And yeah, now if I make everything 1, that means all R, G, B, all three are 1. That means we should get white. See? So yeah, now you understand. Now I think you can understand. So this is the function where we calculate the color value of each pixel. Alright, so now let's see how to make it a gradient. So that means we should get these fragment coordinates like I think this x coordinates of frag code goes from 0 to 800, and the y coordinate goes from 0 to 450. To see if that's true, let's see. I'll use frag code.x here. Yeah, I guess that's what happens. So to get a value from 0 to 1 across this screen, I need to divide this value from the width or the horizontal resolution of this display. At the moment it is 800. Let's see. Oh, okay, I have to add, this is something like a data type issue. I have to add a 0.0 as well. So now you can see this area is white and this area is blue. Right, let's make these things 0. now we can have a clear idea. Okay, this area is black now and this area is red. All right, now to keep things clean, I'll define a new vector 3 which can hold x, y, z values. So that means RGB values. Color, I'll call it pixel color, and how should I define it? I think we can define it like this: 3 0 0 0. Yeah, okay. Now I'll use pixel color. Okay, all black. Now let's try to get some strips. So if I do something like this, let's try to define an if condition. If frag code dot x modulus 50 equals, maybe equals 0, no, not equals, let's say larger than 25, we should return let's define the pixel color above so that we can assign the value as we see fit. Does it have? Okay, wrong operand types. Oh, maybe we should add a 0.5. All right, let's see the help. Now we do have this modulus operation. Do we have any examples? Actually this works. I have to cast this to an int, so add a bracket around that and put int before. And yeah, now I need to make this not 0 0, I should make this 1 1 1. Right, now we got vertical strips. So here what's going on is, if the fragment coordinate modulus, that means divide it by 50 and get the remainder. If that remainder is larger than 25, the pixel color should be black, should be white, that means 1 1 1. Otherwise it would have the default value which should be 0 0 0. That's why we have black stripes down. So this is your next assignment. Write a program using shader toy to display a pattern like this, a checkers pattern basically. Now I have shown you how to use the software, how to use the code, so you have the help and you can use other tutorials or examples in this channel, in that website, and find out a way to render a checkers pattern like this and upload it to the course web. So this is just another way to use image inputs in that program. You can research on that topic too if you like. Yeah, actually not if you like, that is also This is the second part of that assignment. First part is create this checkers pattern, and second part is get an image input and do something like this: merge two images using shader toy. Alright, so now what we saw was like just simple examples of how to write a rendering function. But what about a complex scene like this? Now, as you can see, there are lights, there are shadows, there are reflections, so many things are going on in this scene. And how do we render something like this? So actually the same model, but a more complex program. So yeah, in complex rendering we have to learn how does the lights works. So that's why I put this image here. So when we look at some object, we see the rays reflected, the light rays reflected from that surface. So we see those objects as a result of seeing those light rays, receiving those light rays to our eyes. So this is the normal of the surface, and this is the light ray, and this is the reflected light ray. We can consider them as vectors. So this is specular reflection. Here this surface is smooth. That means it doesn't have any dents or pores in that surface. So as a result of that, all the lights hit, all the lights rays come to this surface, reflects them back. Everything comes perpendicular, everything comes parallel to each ray, and so all those rays reflected also similarly leave the surface parallel to each other. But all the rays are reflected in the same way, in the same direction. But in a diffuse surface reflection, that means the surface is not smooth like in the first case. So as a result of that, even though the lights received in a parallel manner, they are reflected to all the directions. So as a result of that, we don't see clear reflections on diffuse surfaces. So this is how we convey information about 3D shapes in 2D. That means even though, when we render some object in a 2D screen, 2D computer monitor or any other display, even though the screen is flat, we know if we render a 3D object, now that is a 3D object. We can identify that. That's because of this, because we understand the way the light is being reflected. So with that we can perceive the depth of the object. So in shading, there are three models: flat shading, Goro shading, and point shading. So in flat shading, well, actually we can practically see the polygon faces of that object. So it used the same color value across the polygon. So that's why we can see these sharp edges. In Goro shading, it's a little better than in that model. It uses a more like interpolated pixel values across the polygon face, and so as a result of that, the polygonal face edges are less visible than the first case, and in point shading it's better than the middle second case too. So yeah, this is flat shading. This is the least expensive model, and realism is limited and visible polygon edges. So those are the limitations here. But yeah, since this is least expensive, maybe this would be better for mobile platforms, but actually it depends on the game you are developing. So yeah, and in Goro shading, light intensity at each vertex is calculated and then interpolated across the polygon to get value for each pixel, gives a linear color gradient across the polygon. So as a result of that, edges are less visible than flat shading. So that means the color values are calculated for each of these vertices. A vertex means one of these points like this, and then after calculating the color values for each of these vertices, we interpolate them to get pixel value of of a relevant point of that object. So for example, actually this should be 3D, but to make it easier to understand, I have put it in 2D. So this point is 10 and this point is 20, so this point should be 15 by interpolating them, and we can kind of do something like get something like a ratio from the point to that point and this vertex. So like that we can do a calculation. And in point shading, it improves polygonal face edge hiding. So this intensity is now just like before. Here also we calculate the color values for each vertex, and the intensity is of each pixel is calculated by using interpolated surface normals. That means not just the location, not just the relative location, the normal of that point is also considered when we do this rendering, this shading. So therefore it's much accurate, but also much complex and expensive than previous two cases. And the next thing we need to consider in rendering objects are shadows. So the shadows gives more realism and firmly establish the object location in relation to its surrounding. What does that mean? Well, let me show you an example. So here we have a plane, and on top of that let's add some object like this. Let me make it a little more like a ball. Okay, and now because of this shadow we can actually see where this object is, right? Now if I disable that shadow, here select the object and I disable both dynamic shadow. Now we can't really understand whether this object is on the surface or off the surface. So even if I place it like this, now I can't see where is this object is it sitting on this second surface or is it floating above the ground? We can't understand that. But if we have shadows, okay, now we can see it is definitely floating above the ground. So that's the importance of shadows for rendering to increase the realism. And when we consider a shadow, there are two sections, umbra and penumbra, as you can see here. So I'm not really going to do much details about these things. So yeah, now that we know something about shading and shaders, so materials is a wrapper for shaders, defines settings parameters to be passed into shader. So for example, we have a 3D model, and a 3D model has a material, so it is has a kind of a relationship. Inside this material it can contain textures or shader property values, and this material use a shader to actually use these parameters and textures and render the surface of this 3D object. So that is a use a kind of a relationship. And UV mapping, so this means projecting a 2D image to a 3D model surface for texture mapping. So when we get a 3D model like this, we can see the UV map of it in a 2D texture like this. So it's, you can think of it as a conventional map. For example, if you take a world map, even though the world is globe, we can see, we are used to see it as a 2D map like this. And UV unwrapping means like laying out triangles of 3D mesh into a flat surface. And the next part of the lecture is Unreal Engine physically based material system. Actually, I don't think I should do explain these parts here. This is more like engine specific rather than being theory parts, and I have covered extensively these things in other videos I have. So yeah, I'll just skip this part, or maybe I'll just roughly go through them. So in blending modes, no, we have these types. This is opaque, that means it doesn't have any transparency, and this is masked, that means it is either full transparent or non-transparent at all. It doesn't have any partial transparency. And translucent, this is, yeah, this is the translucent. This is wrong, no, this is wrong, this is a mistaken slide. So in translucent we can have partial transparency, so you can see what's behind and also what's in front of the object. Yeah, okay, you can study these things if you like when I upload the slides. Okay, so as we are doing this as an online lecture, you can't ask questions now, but if you have any questions, feel free to comment. And yeah, thanks for watching. So hopefully let's hope that this situation will recover, like in maybe at least in a month, and we can get back to our normal routines. And meanwhile, stay safe and stay inside, don't go anywhere, take care of you and your loved ones in the family. And yeah, see you and goodbye.